Lecture 28 of Physics 72 discusses the second half of Chapter 29 on electromagnetic induction of university physics. The three main topics to be covered are motional electromotive force, induced electric fields, and displacement currents. The specific learning objectives are listed on this slide. Please take time to check them out. Before we begin the lesson, let's review two important concepts from the previous lecture slides. Faraday's law is given by the following. It's E is equal to negative d dt of phi sub b. Now, the left-hand side is the induced electromotive force, or EMF, which is produced by a time-varying magnetic flux. And remember that magnetic flux may be varied not just through the magnetic field strength, but also by increasing the area or changing the orientation of the loop. The negative sign indicates the current direction, which is better explained by Lenz's law. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the cause of said effect. The induced EMF and current will move in such a way that it opposes the change that produces them. The limitation of Lenz's law is that it only provides the direction of the induced EMF and currents, but doesn't really provide details on the magnitude of these quantities. Now, this lesson today will explore how we can quantify the phenomenon of this induction. Induced EMF may arise from movements of conductors in magnetic fields. We begin the discussion with a slide wire generator, which consists of a U-shaped conductor immersed in a uniform magnetic field. In this case, it's pointing in the page. A metal rod, called the slide wire, connects the two arms of the conductor and effectively forms a closed conducting loop. This slide wire is free to move, while the bent conductor is held in place. Initially, there is no current or EMF present in the loop, so at the start there is no purple current yet. It is in moving the bar with a velocity v to the right that we generate an induced EMF, and then the induced current follows. This example provides a microscopic look on how induced EMFs are produced due to magnetic forces acting on the free charges on the slide wire. Let's have a look at the free body diagram of the charges in the slide wire. We consider the positive charges first. Prior to moving the slide wire, the charges are somewhat uniformly distributed along the bar. The movement of the bar, due to a constant velocity and its immersion to the magnetic field, produces an upward magnetic force. The negative charges would consequently experience a downward force, or from F equals QVB. Coulomb's law comes back in the picture, and the charge separation produces an electric field, which produces electric forces that would be downward for positive charges and upward for negative charges. So the magnetic force and the electric forces would be clashing for both cases. The electric force strength is weak as the separation is not as pronounced initially. It only gets stronger as the bar gets more polarized, while the magnetic force remains constant since our V doesn't really change. At some point, the charges will experience zero net force, equilibrate, and stay in place. We know that Fe is equal to Qe and Fb is equal to Qvb for this case since V and B are perpendicular. The upper part of the slide wire A will now have an excess of positive charges, so as you can see here, and then the part of B will have an excess of negative charges down here. We can express the potential difference between A and B as E times L, L being the length of the rod, and isolating E from the previous equation, we obtain VAB is equal to EL, which is also equal to VBL. As we see, the potential difference across the rod is not explicitly dependent on E. In the context of the whole slide wire generator, we see that this potential difference from the metal rod induces an EMF and generates a current along the whole loop. So it's because of this E that eventually you produce these I's. Now, as the U-shaped conductor is not moving, it should experience no magnetic force. It's the charges close to the terminals A and B that got redistributed. So the charges of the U-shaped conductor near A and B. Because of the potential difference, the charges will get redistributed. The moving rod introduces the EMF equal to the potential difference, and as its name implies, generates movement from a lower to a higher potential. So we consider B to be the lower potential and A to be the higher potential, and it's this EMF that brings the charges from B to A, even though B is at the lower potential. Now, The presence of the EMF drives the movement of the current. And just a quick reminder that L, V, and B are mutually perpendicular in this example. Now, unlike the EMF produced by electrochemicals and batteries, the induced EMF by movements of conductors are called motional electromotive force, or motional EMF. Now, say that we know the total resistance of the loop to be R. We can then produce an expression for the current flowing through the whole circuit. It's as easy as dividing the known expression for motional EMF by R, considering that EMF is in units of voltage, and it should provide us with the equation that I is equal to VBL over R. Now, we started with a simple example, just a rectangular circuit. Now, let's try to expand the horizon by describing motional EMF for loops of all shapes and sizes, magnetic fields of any orientation. As with a lot of generalizations we've done so far in calculations involving magnetism, we start with an element line segment and proceed to integrate it along a contour. An element motional EMF is then given by dE is equal to V cross B dot dL. It may come as a surprise that V cross B returns in motional EMF, but that's just because our first example already set the slide wire to move perpendicular to the magnetic field, so QV cross B would just be equal to QVB. The first example deliberately set the rod to be perpendicular to the velocity so that motional EMF looked like a simple product of V, B, and L. We have to take note though that contour integrals always dot some vector quantity to the element segment. Now, we are concerned with how to use this EMF for practical purposes, so let's try to look at closed circuits. This means closed loops, and the general expression for motional EMF is given by E is equal to the closed integral of V cross B dot dL. Recall that Faraday's law showed us a rather different expression with this, being E is equal to negative d dt of phi b. Truth is, these expressions for motional EMF are actually equivalent. If you think about our slide wire generator, sliding our rod increases the loop area, which in turn increases the magnetic flux. The distinction between these expressions is that the integral equation describes the specific case of Faraday's law of EMFs produced by changing the area to change the magnetic flux. The integral equation is rather limited though, because it is only applicable to moving conductors in a constant magnetic field. We must set our foot down and accept that the derivative equation is the most general description of Faraday's law. Let's strengthen our understanding of motional EMFs and slide wire generators with this. Here we have an example, an exact same setup, but we're just including actual values. I'd ask you to read the problem yourself. You can pause the video or the PowerPoint. Now we answer three questions. First of which is, what is the magnitude of the EMF induced in the circuit? We can easily answer this with E equals VBL because the configuration is identical to the first example. Second question, we have to do it in three ways. We're supposed to find the direction induced in the current using all the methods we know so far. That's Faraday's law, Lenz's law, and a zoom in on the magnetic force and how it affects the charges in the moving rod. Finally, we calculate the current running through the resistor, which we can do easily after we solve the first problem. Answering the first question should be a walk in the park. Since V, B, and L are mutually perpendicular to each other, the EMF is just given by E equals VBL sine 90, 90 being the angle between V and V. Plug in the values in the calculator and you eventually get 5.6 volts. The next question asks us to find the direction of the induced current using three ways. So, the first method goes into looking at how the magnetic force affects the charges on the moving bar. Starting with the expression of the magnetic force due to point particles, or F equals QV cross B, let's focus on a positive charge. A simple application of the right-hand rule indicates that F should point upward. This force is then responsible for driving a counterclockwise current since the moving bar is positioned to the right side of the loop. So if that's our starting point, we then move on the top. So it's going to go from right to left, then top to bottom, then bottom back to right. We do get the same direction with Faraday's law. So let's first set the typical convention that a counterclockwise flow indicates a positive EMF. This convention also sets our positive B to point out of the page. With that out of the way, we know that magnetic flux is negative since B is pointing in the page. We also know that the flux becomes increasingly negative because the loop area increases as you slide the bar to the right. This sets the change of flux with respect to time to be negative, and from there, we can indicate that the EMF should be positive. We have a counterclockwise current in agreement with our first answer. Lenz's law tells the same story with how our current is supposed to go. We know that the magnetic flux is increasing, so whatever induced current produced must deliver an out-of-page magnetic field to somewhat counter the change. Using the same convention from the previous slide, an out-of-page magnetic field is produced by a current running in the counterclockwise direction. Before we move on to answering a few concept questions, let's try to address the fact that we haven't really used the contour integral expression for solving motional EMF. I hope you can spare a minute for this, but feel free to move on to the next few examples as the methods we've employed so far are a lot simpler. This explanation paints a clearer picture on how we solve using this integral calculation. Whenever we have a closed contour integral, we can always divide it to integrals which are easier to solve. Since our loop is a rectangle, it would be obvious to split it to 4 contours: C1 top, C2 left, C3 bottom, and C4 the metal rod on the right. Expanding the integral, we have the following. Now, if you look at it, it seems daunting to solve at first, but note that it's only the metal rod that moves, which renders V1 0, V2 0, V3 0. Eventually, those integrals will be 0 as well. You're only left with the fourth integral. And we do note that V4 equals V, and dl4 is just integrating dy from V to A. And we have the following expression. As V, B, and dy are all perpendicular, we will get our familiar result, VBL. Try your understanding with a few concept questions. Here we have 3 conducting bars immersed in a magnetic field pointing into the page. All rods move at the same velocity v towards the right but are oriented differently. The task is to look for an answer which best describes the strength of the induced EMF on the 3 rods. You're going to compare the strength of the induced EMF. You may try to pause it, or you may pause it to try it on your own. So the clue here is you don't really need to solve explicitly. You just have to remember that EMF is proportional to V cross B dot L. Move on to the next slide to check your answer. Now the correct answer should be B. We get this from remembering that the induced EMF is proportional to V cross B dot L. For all examples, V is perpendicular to B, but the lengths are oriented differently. The vector V cross B points up and is dotted to L. The more aligned to the y direction the bar is, the stronger the induced EMF is. The correct ordering is B. It's worth noting that there is no EMF for 3 because V cross B is already perpendicular to L. This third example explores a case where we actually solve for the induced EMF and currents of a slidewire generator where the bar is slanted. No specific quantities for this problem, we're just going to focus on how the trigonometric functions come into play. So I ask you to read the problem again, pause the video if you have to. So what's important for this part is we have to take note that B in this example is pointing into the page, so just in case you forget. While it is a motional EMF problem, we can't just jump straight to E equals VBL because L is slanted. We start with the closed contour integral expression for EMF. As with previous examples, the U-shaped conductor is static, so the only part of the closed contour integral that contributes a non-zero term is the slanted bar. Next step is to verify that V and B are perpendicular, so the cross product is just VB with the vector pointing up. Now, let's emphasize that the vector resulting from the cross product of V and B is not parallel to any part of dl, so we can't just do away with the cosine term arising from the dot product. From what we know so far, we can then simplify the closed contour integral to VBL cosine phi, phi being the angle between V cross B and L. A quick rundown of geometry, as you can see in the figure, gives phi as 30 degrees. Now this completes our expression for EMF, and we get the current by just dividing what we already have by the resistance R. We can see that for the cases where the bar is slanted, we have to consider an added cosine factor compared to what we got from previous expressions and examples. We now move on to another method of inducing EMFs and currents. So far, We took advantage of moving conductors and in turn changing the areas to change the magnetic flux, but soon you'll find out that there is a way to induce EMFs without moving the conductor itself. This explores varying the magnetic field, and in turn, we see an unexpected symmetry between electric and magnetic fields. Now, we arrive at the most important slide in this lesson. This part can be confusing if we cram all the knowledge at once, or if you just look at the graphic blindly. As such, let's go through the graphic on the left step by step, and I count a total of 4 steps. The story begins with a solenoid or the black coil with a cross-section area A and a current I being delivered to it. Let's call this step 1. From Ampere's law, we know that this solenoid, which we assume to be tightly wound, will produce a constant magnetic field for as long as the current is also constant. We call this step 2, and we have nothing new so far. Now we turn to our attention to that bigger loop with the galvanometer, that yellow loop. Remember that our goal is to induce some sort of current I prime, and take note that this I prime is different from I, and this I prime has to be on the bigger loop. Faraday's law tells us that we can do that by varying the magnetic flux through its area, which is already being provided by the small solenoid as derived in step 2. Now, without moving anything in the solenoid, how do we go about this? Going back to the magnetic flux, we have phi B is equal to B times A times cosine phi. Phi being the angle between B and A. But then, since B is already parallel to A, phi should be equal to 0. Okay? We now know that, by now, the magnetic field the solenoid has is equal to mu naught times N times I. So the magnetic flux is just mu naught times N times I times A. This is where step 3 comes into play. We take note that the magnetic flux through the solenoid is the same magnetic flux through the big loop, since big loop isn't really getting its magnetic field elsewhere. If we change the magnetic flux of the solenoid, then we consequently do so for the magnetic flux of the big loop. Looking at the time derivative of phi B is equal to mu naught times N times I times A, we reinforce that the coil density N and area A should not change, because that would mean moving the conductor. If you move small n, you're tightening the coils or loosening it. If you change the area A, that means you're distorting the cross-sectional area, and that's not what we want. This leaves us with no choice but to vary the solenoid current I. And that's our step 3. We can now have an expression for an induced EMF on the big loop from Faraday's law, given by this equation. E is equal to negative d dt d phi B, which is something we already know. But then we have an expression for phi B already, and that's just given by mu naught n times A and di over dt. Remember that you cannot vary n and a with respect to time. From there, we can get an induced current I prime, which is different from I, and it should be given by I prime is equal to E over R. And then R there should be the total resistance of the loop. Now, taking a step back, we see how the change of a current in one conductor, the solenoid, drives a current in another conductor, the big loop, in a multi-step process. This is electromagnetic induction in action. Now, if there's a current produced in the big loop, you may wonder what force drives the charges to move around it. The big loop itself isn't moving, and it isn't immersed in a magnetic field in the first place. If magnetic force is out of the picture, it can only mean that an electric field was induced due to the changing magnetic flux. This magnetic flux was changed via the solenoid. Putting those words into an equation, we have integral of E dot dl is equal to epsilon. Now take note that the I in the diagram, this I here, is not the current that's induced, I prime, but rather that's the current of the solenoid. So let's try to settle some things about this induced electric field. Okay? The work done by the induced electric field per unit charge is given by the induced EMF. And then this induced EMF has units of voltage. I've taken special consideration to say that the induced electric field and not just electric field. This induced electric field produced by a changing magnetic flux is not the same as the electric field produced by charges via Coulomb's law. Recall that the Coulomb law electric field is conservative, that is, its contour integral along a closed path is always zero. But then for the induced electric field, it's not equal to zero, it's equal to the induced EMF. Our induced electric field here is not conservative. We can now connect the contour integral of induced electric field to Faraday's law with this equation, negative d dt of phi b, with great care. As the most general case of Faraday's law is its equality to the negative change of magnetic flux with time, we can only equate this to the integral of E dot dl when the integration path is stationary. Therefore, this integral here is a special case. We've encountered this limitation before, albeit a bit differently, with motional EMF and the integral of V cross B dot dl. So I'll just redraw it for comparison's sake. What we had a while ago is actually just another special case of Faraday's law. But then the one I doodled is the special case wherein your conductor is moving, and the one that's written on the left is when the conductor is stationary. How can we then extract an expression for induced electric fields? Well, taking a page out of Gauss and Ampere's playbook, we can easily do so for symmetric configurations. Our big loop on the left is circular, and by choosing dl to be parallel to E at all points on the contour, we can pull E out of the integral after dotting it to dl. We then end up with a very familiar circumference factor, well, which we can conveniently transfer to the other side. So let's run by quickly on some of the properties of the induced electric field. You already know that it's non-conservative because its closed contour integral will not be equal to zero. This immediately leads to an admittedly advanced topic, it being a non-electrostatic field. Despite this, we can still associate an electric force with our usual equation. A comparison between electrostatic and non-electrostatic fields can be seen in this slide. You may pause it for a review. Now, before we move on to the last topic, I promise that we will try to shine light on the symmetry of E and B. From Faraday's law, for induced electric fields, we have this equation. From the general definition of magnetic flux, we have this equation. Now, the stationary conductor case for Faraday's law gives us this expression. It's basically a combination of the first two. So we have the integral of E dot dl is equal to the negative time derivative of the magnetic flux, or B dot dA. Upon observing this equation, it states that the time-varying magnetic fields, here on the left, can be the sources of electric fields. This is one of the four conclusions that are stated in James Maxwell's famous Maxwell equations. Right, we're down to the last topic for this lecture. So it turns out that Ampere's law, that you know so far, is incomplete, and we devote a section of this lecture to put him in his place. Now, we have a small spoiler. At the end of this subsection, we're going to show that time-varying electric fields are sources of magnetic fields. This is the mirror counterpart of Faraday's law, and the beginning of a beautiful journey to electromagnetic waves. Going back to our old lesson on capacitors, have you ever wondered how the current actually passes through the capacitor? Let's consider the case where we are charging the capacitor. The current entering the positively charged plate is the conduction current IC, as we see here. The two conducting plates are supposed to be insulated from each other, so there should be no conductors in this area. So now the question is, if they are insulated from each other, how can these charges flow? Now to start, we apply Ampere's law to the circular path shown here. So this is the circular path, the one with dl. Just highlighting that part. Let's also choose two surfaces that are enclosed by this path. The plane surface, the one here, and the bulging surface, the one that's parked here. Let me erase this first. Now, Ampere's law for the plane surface gives us B dot dl is equal to mu naught I enclosed. For the planar surface, that I enclosed is simply just IC. Ampere's law for the bulging surface gives us quite a hiccup. The right-hand side will be equal to 0 because there's no current that's enclosed. So if you think about again, there should be no flow of charges in that area because the moment you do so, the capacitor fails to work. This becomes an issue because the left-hand side for both surfaces are actually equal. It's the same circular path and it's the same magnetic fields. It's the same contour integral. We have a contradiction on our hands. So the question is Ampere's law even correct? Instead of cancelling the law, let's try to save it. Turn your attention to the bulging surface again, and let's try to explore what we know so far. Something about capacitors and something about electric flux. As the capacitor charges, the charge given by Q is equal to CV accumulates on both plates. Now this increases the discrepancy of positive and negative charges. So as time goes by, more and more positive charges reside here, and more negative charges reside here. Now, this discrepancy actually strengthens the electric field in between, the one here, and in turn the electric flux. From the known capacitance, equations of parallel plates, as well as the potential difference between the plates, a little bit of algebra leads us to an expression of charge being equal to epsilon naught E times A, but then we know E times A to just be equal to the electric flux. From this, we can obtain an expression of current in the form of the time derivative of charge. The right-hand side describes that it is a time-varying electric flux that drives this current. So as you can see, the left-hand side of the last equation is actually your current already. So it's some form of current, and this current is proportional to a time-varying electric flux. Now, let's go back to the plane surface. We already have the usual expression of this conduction current being IC equals dq over dt. And also, we have an expression for the current enclosed by the bulging surface. It's just the one that we derived. Let's call it slightly different. It's I sub d. This I sub d is determined to be the displacement current, coined by Maxwell. It's an imagined current, or a fictitious current, between the plates. So what we have so far is Maxwell tried to save Ampere's law by coining this displacement current to try to resolve the contradiction from a few slides back. I'll get to that in a bit. So as displacement current is dependent on electric flux, if you want an expression that just depends on the electric field, then divide both sides of the equation by the area. And I divided by area is a familiar term. We have a familiar term for that already, called the current density JD. So you may pause the video if you want to see how it was derived. So let's now try to correct Ampere's law with this extra term. So in this equation, you have the integral of B dot dl is equal to mu naught times IC. This is the conduction current term, and this is the displacement current term. Both of these currents should be present in the enclosed or what's enclosed by the surface defined by the contour. Then we have our condensed version being equal to this. It looks nicer. Now, let's go back to the planar and the bulging surface. The corrected equation will make sense for both cases because at the planar surface, I sub d is equal to 0. But then the only thing that will be present in the planar surface will be IC. Now, if you look at the bulging surface, it's IC that will be equal to 0, and it's the changing electric flux that dominates the current term. So basically, ID. So what we have so far accounts for both of the currents and in both of the surfaces. Now, assuming that the charge won't leak out of the capacitor, whatever current runs through the wire should have the same value as the displacement current in the bulging surface because charge should be conserved without leakage. From the first equation, we can see that the currents and changing electric fields from flux are the sources of magnetic fields. So as we may not have enough time for this video, I invite you to study the problem yourself. You may pause the video if you wish to answer. The next slide provides the complete solution. So I'll flash the solution. You may pause to check your results. Before we end the video, I want to show you a glimpse of what's to come after our lesson on inductance and RLC circuits. You may not realize it since some of the equations have been discussed at the start of the semester, but we have actually covered all of Maxwell's equations already. The first two that you see here are Gauss' law for electric and magnetic fields. And the last two Maxwell's equations are Faraday's law and the modified Ampere-Maxwell's law. Now, as a parting gift, I want you to see Faraday's law and Ampere's law side by side. In the absence of currents, IC should be equal to 0, and Ampere's law reduces to a single term on the right-hand side. Looking at this part, the time-varying electric fields will produce a magnetic field. And for Faraday's law, a time-varying magnetic field will produce an electric field. So what do we have here? Time-varying fields produce each other. From these equations, lay the foundation for how we currently understand light and how we perceive our world. I hope you're excited for the next few lessons, and thank you for listening.